Hey everybody, here is the lesson covering how to find characteristics of exponential and logarithmic graphs. Top here we have exponential, at the bottom we have log, and then over here we have a couple of each. In this top section it says, in this unit we'll be covering exponential and logarithmic functions, expressions, and equations. Exponentials have an blank as their blank, while logarithms are the blank functions to exponentials, most commonly with a blank of 2, 10, or e. Up here at the first blank we have, it says exponentials have an x as their exponent. So it's very easy to see when we're looking at an exponential equation or function because you'll see the x appear as the exponent. While logarithms are the inverse functions to exponentials, most commonly with a base of 2, 10, or e. You can see here on this exponential, this is an exponential with the base of 2, and x is its exponent. And then you can see here, this is a log with the base of 10, and then this is just what goes on the inside of the function. But this is our parent function for base 10. If you have one that doesn't have a base, put a little note here. If no b, b is 10. So sometimes it will show you this, or sometimes it'll actually just do this, log of x, and those are actually the same thing. So if there's no base written down, the base is 10. If there is a base written down, it'll either say 10 sometimes, or it'll say any other number that would also be the base for that. The last sentence here says, in the real world, exponentials are used in finance and investing, while logs are used in STEM. These are the most real world helpful type of functions that you'll cover in Algebra 2, or probably mostly in high school math at all. Exponentials are really helpful when you're looking for things like investing and looking at compounds and how quickly and how often interest rates compound the money that you have in your account. And then logs are used a lot in chemistry if you are looking to be a scientist. We're going to go over the words here. I am going to go a little quick just because we've already covered all of these characteristics before. The only one that is a little not recent, that would make sense, but you know what I mean. The one we haven't seen in a while is this one. The rest of them we've seen recently multiple times in all of our different function videos. So first we have x-intercept. That's where we cross or touch the x-axis. As you can see, it does go flat here towards the x-axis. I'm going to highlight the x-axis for you. It is right here. So you can see it doesn't cross over. It does go right up against it and then goes up this way. So we're actually going to put none for that. It does not cross over or touch the x-axis. It does, however, cross the y-axis. It's right there, and that is at 0, 1. Next down, we have restricted values. Remember, restricted values we first learned about in rational functions. They are wherever the domain of our graph does not exist. So it's anywhere along the x-axis that the graph doesn't go. If you look at our graph, you can see we are over here. It does go in this direction, and it keeps going. Then it goes up in this direction. It is going all the way to the left with an arrow towards negative infinity, and all the way to the right with an arrow towards positive infinity if we're looking along the x-axis from left to right, not up and down. So it's uninterrupted. There is no value that it doesn't include, so there are no restricted values. And that's going to be true for all exponential functions unless they have a given domain. Moving down here, we have domain and range. I'm going to label those here. Our domain for exponential functions, because we have no restricted values, is going to be all real numbers. And you can write that like this, or you can say all real numbers. And that'll be true for all exponential functions, unless otherwise stated that you have a restricted domain. The range will be related to their asymptotes. I'm going to do that one first, actually. Right here where it says asymptotes. Remember, asymptotes are invisible dotted lines that our graph normally approaches and doesn't cross. It can cross them if they are horizontal, but normally does not. If you look at our graph, it's wherever it flattens out. See, it gets flat right there. So our asymptote, I'm going to draw it with a highlighter here, is going to be right here along this axis, like that. And that would actually be at y equals 0. So this is a horizontal asymptote. I'm going to call that HA at y equals 0 because that's where we flatten out. We flatten here, and that is at 0 on the y-axis. We don't have a vertical asymptote. We would know if we had one because there would be a restricted value where we don't exist, because that is what a vertical asymptote is. But we don't have any of those, so we're going to say no vertical asymptote. This will be true for all exponentials. They will never have a vertical asymptote, and they will always have a horizontal one. It won't always be at 0, though. This one is at 0, and the easiest way to see where your horizontal asymptote is it's actually going to be the number back here behind your exponent. We call that k. This number back here will tell you where your horizontal asymptote is. Because we don't have a number back there, that number would have been 0, and that's why it is y equals 0. Now, circling back to our range, the easiest way to get the range is to, well, look at your graph first off. It's either going to be above the horizontal asymptote or below the horizontal asymptote, one or the other, and it will be approaching the horizontal asymptote on one end as well. As you can see, ours is above, it's up here. So our graph includes everything from the horizontal asymptote at 0 up. So it's anywhere between 0 and infinity. Remember, I'm going to use parentheses around anytime I have an infinity because you can't reach infinity. I'm also going to use a parenthesis around this 0 because they don't actually touch 0, it's just approaching 0. The other way to write this, you put or, you could also write it in inequality format. This is all the numbers that are bigger than 0, so you could also say y is greater than 0. That's another way to write this. Same range. Good. Moving over to the right side, we have extrema, intervals of increasing and decreasing, rate of change, and end behavior. Looking at the extrema first, extrema, remember, here we go, are maximums and minimums. This would be a maximum, and that would be a minimum. So it's when our graph changes direction, it's increasing and then decreasing, or decreasing and then increasing. As you can see, our graph actually is increasing the whole time. There is no point where it starts to decrease again, or in the first place. So we actually don't have any extrema. We're going to put none. And then for interval of increase or decrease, we'll only have one or the other because we don't have any extrema. Our graph, as you can see, is going up towards the right. So this would be an interval of increasing. I am going to list them both, and then next to decreasing, I'm just going to put never, or you could put none if you prefer. Increasing, it's increasing forever, meaning it would increase along our domain, which is from negative to positive infinity. The rate of change is referring to a rate of growth or a rate of decay. For our graph, the easiest way to look at that is if we are growing, it's going to go from flat to steep. And if we are decaying, it'll go from steep to flat. And I'm actually going to have us write that right up here. Growth and decay. If you are growing, you are going from flat to steep. And if you're decaying, you're going from steep to flat. There is also a way to figure it out without looking at the graph if you just have an equation. And for that, you're going to look at your b value, which is the one that has the exponent. In this case, it would be a 2. If your b value is greater than 1, you are growing. And if your b value is less than 1, it cannot be negative, so it's going to be bigger than 0. So if it's between 0 and 1, it is decay. And we'll go over that much more later on. So looking at our graph, we go from flat to steep. So this would be an example of growth. And last but not least, we have our end behavior. The end behavior, I'm going to label that L and R for left and right, is always going to be for these going towards the horizontal asymptote on one end and going towards infinity on the other. Looking at our left end, the left end for this one is the one that's approaching our horizontal asymptote. So as on the x value, it's going towards negative infinity. Its y value, you can see, is approaching 0 because it's approaching this asymptote right here. You might also notice this does match the left side of our domain and range. That'll be true so long as your front number is positive. Our right side, looking at the right side, as x goes in the right direction, so it's towards positive infinity. If you look at our y, it's actually pointing up. The graph is going up, so I would go to positive infinity as well, which again, you can see matches. Right there. Sorry, I had a brain fart. And there we go. Hopefully this feels like a good review of this information that we've seen a couple times this year. Scrolling right on over here, what we're going to do is you're going to try number 1. So go ahead and pause, try number 1, and then come back when you're ready to look at it, and then we'll do the same thing for number 3. Here is number 1. Go ahead and check over what you have. For our x-intercept, I didn't feel like graphing it in the calculator, so we're just going to estimate and say it looks like it's negative 1/3. Obviously, if you wanted to graph it in Desmos, you could, and then just look at the x-intercept. It's not going to be exact, but there's a good enough approximation. Y-intercept was at 3. We are growing because we go from flat to steep. Another way to figure that out is look at the equation. You can see there, the number that has the exponent is b, and in this case, b was 1. Well, sorry, 7, which is greater than 1. There you go. Restricted values, we had none because they're never going to have any. Same for extrema, for exponential functions. Our horizontal asymptote, it got flat. Sorry, I forgot to highlight it right here. And that is at -4. So horizontal asymptote at y equals -4. And we can also see that number from the equation. It's the number back here. Our increasing and decreasing, we are increasing the whole time. It's going up. So I put negative to positive infinity. Remember, it's going to match the domain for these. And then obviously decreasing, I should put none. And behavior on the left end, as we're going towards negative infinity, the y value is flattening out here at -4. And then on the right side, as x goes towards positive infinity, there we go, y is going up towards positive infinity as well. And just a reminder, that is going to match your domain and range like this. There's the left side and the right side, so long as your front term is positive. And then last but not least, our range, it goes above the horizontal asymptote, whether it's going to be above or below. This one is above, so it goes from -4 up. So you can say it like this, or you could say that y is anything greater than -4. Just a reminder, it's not equal to, because we don't equal these asymptotes, we just approach them. Good. Going to the bottom, go ahead and pause, try number 3, and then come back when you're ready. Here is our last one here over exponentials. We did not have an x-intercept because it did not cross the x-axis because we had our horizontal asymptote at 0. The y-intercept, I got that from graphing it in the calculator. This one, you could see it does cross over the y-axis right there. It's just really, really, really close to 0. It was at -1/625, which is a pretty small decimal. Our rate of growth or decay, we have a growth function. It goes from flat to steep. I didn't mean to give you all growth. I need to fix that for next year. Here, it doesn't look like growth though, right? Because it's actually going down. And the way we knew that is because it went from flat to steep. Or if you look at your equation, we're just looking at the number, and the number here is a 25, which is bigger than 1. The reason that it's facing downward like that is because of this negative sign that impacts the direction that it points, because it reflected over the x-axis. Horizontal asymptote, it crosses, or doesn't cross, but it approaches at 0 here. I have highlighted that for you. You can also see it in the back of the equation. There was no number back here, so the number was a 0. Never any extrema, never any restricted values. Increasing or decreasing, we're pointing down, so we're decreasing for all of our domain. Left and right, on the left side, which I forgot to label, sorry. There we go. On the left side, as x is going in the negative direction, y is approaching that horizontal asymptote at 0. On the right side, as x is going in the positive direction, y is going down in the negative direction. This is the time where, see how these don't match this time? Here, here, and here, those don't match this time. It's going to match this way, and that's because of the negative number in the front. And so our domain, our real numbers, our range is everything less than 0. So we're always going to start with the smallest number first, so negative infinity down here, up until 0. Or you could say that's all the numbers less than 0, so y is less than 0. Perfect. Let's go back to the first page here and then go over the logarithmic one. Remember, this is the inverse of an exponential, meaning everything is just going to swap the x and the y. So if our original x-intercept was none, that means now our y-intercept is none. If our original y-intercept was 0, 1, our x-intercept is going to be 1, 0. Let's see that right there. 1, 0. These also do not have any extrema. They are, though, going to have restricted values, and that is because of the asymptote. So I'm going to go to the asymptote first, and then I'll come backwards. Asymptotes, remember before we had a horizontal asymptote, but no vertical asymptote. So now we're going to have the opposite. We're going to have a vertical asymptote, but no horizontal asymptote. I'm going to say no horizontal asymptote. But remember, I'm just swapping with exponential. I am going to have a vertical asymptote at x equals, and then wherever it goes flat, here it goes flat right there. See, that's flat right there, which is at 0, right? Because this one was y equals 0. So here, I'm going to just draw that on there. There we go. And that's at 0. This is going to change our restricted value situation. So the restricted values are going to be wherever the graph doesn't exist. For logarithmic functions, because they have a vertical asymptote, they are going to have a restricted value at that vertical asymptote. So for this case, our x cannot equal 0. It also can't equal anything where it doesn't exist, which is on that left side of 0. So we would also say that x cannot be less than 0. It's going to be whatever half of the graph doesn't exist. And then domain and range is super easy compared to here. We're just going to swap. So before our domain was all real numbers, now it's going to be our range. And that's going to be true for all of them. You can see here from at the bottom here all the way up forever. And then our domain, there we go. Before, let's see, we swapped it. So before our range was 0 to infinity, so now our domain is going to be 0 to infinity. And you can see that right here, it starts here at this asymptote and then goes this way. So it starts here at 0 on the x and then goes towards this arrow, which is going towards positive infinity. So 0 to infinity, or you can say x is greater than 0. You'll notice when you're looking at these or when you're writing them down, your domain is going to be the exact opposite to your restricted values because the domain is saying where you do exist and the restricted values are saying where you don't exist. For increasing and decreasing, here we go, mark those down. These are not going to be subject to being backwards because it doesn't mathematically make sense that way. If you look at increasing, here, that means I'm going up. I am going up the whole time. So I'm going to go for the entire domain, which is now from 0 to infinity, not from negative to positive infinity, because I'm looking at the domain still. And it's never decreasing, so I just put none, or you can put never. And then our end behavior, I'm going to label left and right. These are also going to swap. So looking at the left side, so I'm looking at x. On the left, x is going towards this vertical asymptote at 0. And the y value is pointing down. It's going in this direction down here, which means it's going towards negative infinity. You can see that does match here, right there, because we have a positive. If this was negative, then it would be the opposite. And then looking at the range, we're going in the positive direction on x is going towards infinity, and y is going up So it's also going towards infinity, which matches right there. And there we go. So main takeaway, swap it with the exponential because they're inverses. So you just change x and y, and then resolve obviously for y. And most of the characteristics are going to match the same pattern as they do up here. So let's look over here. Go ahead and try number 2 and then come back when you're ready. Here is number 2. We have our x and y intercept are pretty easy to see on the graph. I just estimated that y-intercept. Our restricted values, remember, are where the graph doesn't exist. It stops existing at -3 and does not exist on this side either. So I put that x couldn't equal -3. It cannot be less than -3. And then here is our vertical asymptote right there. It goes flat right there at -3. We are increasing across our whole domain. Our domain is going to start at that vertical asymptote, so it's from -3 to infinity. We're never decreasing. And behavior, here is the left side and the right side. You can see on the left, we are pointing towards -3 for the x, and then it goes straight down for the y. And then for the right side, it's going up and up. Our domain, like we already said, it exists here starting at its vertical asymptote. Well, starting just to the right of the vertical asymptote. It's from -3 to infinity or greater than -3. And then the range is always going to be all real numbers. Perfect. Hope this helps. Bye.